And thanks for being here this morning too. It's also your last morning, right? Lecture, so it's good. Okay, so today we go back to QCD and coordinated with Ian. What we want to talk about is a bit the problem which I vary with my great skills, artistic skills, I depicted in the top blackboards. So the idea, what we developed a bit, not talked much actually, is the idea that you can have a picture of what's going on in collider physics, in particular in PP collisions, by using this formula that we discussed already a few times, where you do the convolution of the part of distribution function times a cross-section, which is a short distance one. So the idea that at a scale mu f, which we set somewhere here, we divide what happens before mu f and we put it in the PDF in an inclusive way, and what is in the short distance coefficient, we put in the short distance coefficient, short distance cross-section, Bartoli cross-section. So this is a factorization theorem, and what we learn in class is that we can compute this order by order in perturbation theory. So we discussed the leading order computation. In the notes that I put on the web, there is also a next leading order computation done in the limit where the top loop is shrunk. So we reduce a two loop into one loop computation. And what we want to do today is to link this picture where only very few partons at the end are present in the final state, in the calculation, right? When I go leading order, there is nothing else than the Higgs. And next to leading order, I might have an extra parton, and so on. So my description becomes more detailed, but still very, very far from what happens actually in a true collision at the LHC. Okay, so there is obviously some at the LHC. What we will get is certainly a Higgs at some point here. Okay, but then before that we will have a lot of radiation in the final in the initial state, so-called. So before creating the Higgs, there will be radiation coming from what we call initial state radiation. And then in the Higgs decay, also there will be jets, leptons, and so on. So you have all seen these images of event reconstructed LHC, and they don't certainly look like that, right? They look much more like this, with many, many particles, orders hundreds, even thousands of hadrons in the final state. So now the question you might ask is, okay, if you want to just, for example, count the number of Higgses that I will produce, this is okay. If I want to count also the number of Higgses in a given PT, this is okay. So somewhat what the final output of an experimental analysis is somewhat compliant with this picture that a theorist has in mind. Because at the end, you want observable that you want to communicate to others, and you simplify them. Cross-section for TT bar, cross-section for the X, differential cross-section, and so on and so forth. The problem arises, however, because when you want to get these numbers and compare with theory, actually, anyway, you have to go through here, first of all. Second, there are some observable that in any case, I will need a full exclusive description to be accurate enough to be able to describe and then compare with the experiment. So this description, I call it fully exclusive. And this one, I don't put any adjective, but I call it inclusive. And it's inclusive, as we said already several times. For example, in the up to the mu scale, which is in the PDF, everything is integrated out here, right? That's what we said. All the emissions which happen in the initial state are integrated out in this f up to a given scale. So the question is there a way, right? So is there a way to link these two pictures in a rigorous way? So is it possible to unravel, right, all the inclusiveness which is implicit in this formula and make it exclusive? Okay, so the way you can see it, actually, one way I particularly like to, as an example in my mind. So when I talk about inclusive, I mean that I'm summing over many final states with many possibilities, right? So for example, here I include 100, 101, 102, 103 values in all directions and so on. So here I'm very much summing over final state, okay? Summing over what I call stories, okay? Here I'm summing over possible stories, possible things that can happen, and sum them all, and I compute as an inclusive object, right? Here, what I'm doing, I'm actually picking up one of the zillions of stories that can, when summed, give this result. Okay, I'm picking one. So I'm doing a simulation for the LHC. I generate 1 million stories, or 1 million events. Each event is one possible story how the PP collision came to produce a Higgs and then decay. And what I want is that this, the way I associate a story respects the probability predicted by QCD. Okay, so I generate a PDF, a probability density function, and then I generate events with the probability density function calculated from first principle. And then I pick one random number, and I associate a story with the probability, right, with the correct probability. Is that clear? So we say we generate awaited events. So we generate events as if they were in our Monte Carlo, as if they were like generated by QCD, by nature, right? So when nature produces an event, it produces an event with the right probability, right? Because you generate 10 events. Let's say you do a plot, right? You have an observable here, and then you generate, 10 events like this. Oh, okay. Something like that. And this distribution of events, after many events, will follow the PDF from theory, right? So what an event generator does, it generates an event following a given probability, and this probability are determined by calculation, by this object, the f, and so on. Okay? So now, today, I'll try to explain how this works, how we can actually do that, right? Because if you ever done, again, a computation in QCD, you know that 2 to 2 is easy, 2 to 3 is difficult, 2 to 4 is impossible, right? I mean, so to do by hand, I mean. So you realize that obviously we cannot use the normal techniques that we learn in school to compute something like that. It will never work. So my first important step towards that, I will try very briefly to recall the elements of an extra linear order computation. And to do that, I'm using the simplest possible case, which is Z that goes to 2 quarks. So there are a leading order, there is a Born contribution, right? A quark, an anti-quark, and then an next leading order, I have virtual connections with the gluon, and which are interfered with the border. So when I square them in this way, right? So the order of this diagram is alpha s at the end. And then I have real, so these are the virtuals. And then I have real corrections. And real corrections are squared with themselves. Okay, so there are two diagrams which are summed and squared. And this also is order alpha s. Right, this alpha s because it's only one side. So if you want, actually, I think you are familiar with that. You can think of a diagram like this, right? And with various cuts, with different cuts. So if you cut it here, you get a real contribution. And if you cut it here, you get a virtual contribution. It's always the same diagram where you cut it in different ways. Okay, so the real and the virtual are different cuts of a two-loop diagram. Okay, so there is an important theorem in quantum field theory that goes under the name of KLN theorem, which tells me that if I'm inclusive enough in my final state, then the sum, therefore, for example, in the cross-section computation, so if my observable is sufficiently inclusive, the template observable is the cross-section, which is, we are fully inclusive, okay? Here, this cross-section that you define, you want to compute here, is sigma of E plus E minus going to hadrons, which as a definition, you cannot almost be more inclusive than that, right? You take all events which have at least one hadron in the final state. That's your definition. And then you try to compute it perturbatively. So this KLN theorem tells you that order by order in perturbation theory, if you are inclusive enough in your observable, the IR divergences and the collinear divergences will cancel. Which means that your cross-section is infinite safe, is finite. There is no finite is not really a good word, but let's say there is no leftover sensitivity to any cutoff in the infrared. Yeah, right. Okay. So you're not sensitive to what's happening in the infrared. So thanks to this theorem, whatever infrared sensitivity you have in the virtual, you will have the same with a minus sign in the real and vice versa, because I know that they cancel. So let me only compute the real. I don't want to compute the virtual today. Okay, so let me compute the real, and even the real are a bit annoying. Okay, so let me do a simple approximation. So let me rewrite the NLO. So the NLO cross-section will be M3 squared d phi 3. No, 3 is the number of particles in the final state, plus 2 real M2 Born, let's say, the Born amplitude, the virtual amplitude in d phi 2. Right? So that's the complication. The complication is that here the divergences arise from when I integrate over phase space. Here the divergences are here inside the virtual. So the two phase spaces don't match, and therefore I first have to do somewhat the integration on the phase space here to see the divergences, which then I can cancel with the divergences from the loop. Right? So there is no, I cannot put everything under the same integral apart from here and cancel that at the integrand level, because they live in two different phase space. So what then I have to do the integral or part of the integral here in such a way that I can take out this one-dimensional extra phase space that I have here, and then I can cancel the divergence. Okay? Okay, so the real amplitude So as I said, there are two diagrams like this. Okay, so when I write them, so let me write the two diagrams. So let me call P and the P bar. And then let me call kappa the gluon. Okay, so I get U bar P epsilon that slash minus G minus I P plus kappa. Gamma mu is the vertex P bar. And then there is a color matrix plus the other diagram. Okay, so there are two diagrams. There is a minus I here because I'm the momentum P, right? The momentum P plus kappa is opposite to the fermion flow, so there is a minus 1. So that effectively there is a minus there. And then I do one approximation. I say that kappa, the modulus of kappa is much smaller than P or P bar. Okay, so I use this soft approximation. So if I'm using the soft approximation, then I can somewhat neglect the kappa, not in the denominator now, but I will neglect the kappa in the numerators. So let me collect here. So I get epsilon P plus kappa gamma mu. And then in the denominator I have P kappa minus gamma mu epsilon 2 V P T A. And then what I'm saying is, so the denominator, right, so I'm thinking massless quarks, okay, so P square are 0 and P bar are 0. So notice that the only thing that, so this minus, we explain it, and then there is an ordering which is different, right? Because first the gluon is here, and then it's there. So once is before the vertex, and once is after the vertex. That's also what matters. So the ordering here is not the same. Okay, so now what I do, I neglect kappa in the numerators because this kappa is much smaller than P. Okay, so I neglect these terms, and then I use the Dirac equation. Okay, so here notice that the P of this spinor is after epsilon. So I have to change the order of the epsilon slash and P slash to hit P slash with U and cancel it, right? But when I do it, I do the anti-commutation, okay? And then I get a G mu nu, right? Twice G mu nu, which gives a P mu here, right? So I exchange these two, and here also I exchange these two. And by exchanging, the P slash cancels by equation of motion, and they're only left with the G mu nu, right? So this is an important result. And the result is that I get an expression which is amazingly simple the 2, remember there is a 2 coming from the 2G mu of the anti-commutation relation of the gamma. So the 2 cancel numerator and denominator. And I'm left with this expression, which is really the result that I care. So you see, in one line, we got one of the most important results in soft QCD, right there, right? So this term here has a name, because it's so important. Things which are important get a name. And this is called iconal. Is the iconal and the amplitude level. There is an iconal and amplitude level, and an iconal and the amplitude level square. But now you notice something very, very interesting right away. What do you notice? First, this term factorizes over the Born. So when the gluon here is soft, okay, is actually the result of the amplitude level before a square. Okay, so before a square as factorized in this way. So there is one term here in front of the Born. The other thing that you notice is that here you have a string of gammas. Gammas is the spin, right? Gamma reflects the spin information of the fermions. Here, the spin somewhat is all mixed up because you have a trace of that. Here, in this term, there are no gammas. The only gammas that you have are in the Born term, right? So that means that this term does not touch the spin. It's spin independent. So it doesn't know whether here I was actually producing 2 quarks, quark anti-quark, or squark anti-squark. There is no trace on this term of the spin of the emitting object. So this is really interesting, right? And is a fundamental. It turns out that this object is fundamental. So let me erase here. Do you have questions? Did I make any use of typo and mistakes, or can I erase it? So now this iconal term here, this amplitude, is actually all I need now, right? So I square it. So let me square it here. So my sigma QQ bar G is, I square the T, right? I take the trace of TATB, yes, and get CF. Then I get GS square sigma QQ bar Born from here. And then I have a phase space on my extra gluon. So I factorize the phase space in the soft limit with the phase space which is like the Born, phi2 and A included together with my amplitude, and I rebuild the Born cross-section in front. And then I square this term, which is easily, right, seen that this, you get this very simple expression here, which is also called iconal, but this is the square level. Okay? The square gives 0, okay? Because you get p mu p nu epsilon mu nu is a g mu nu, and then it's p square. But then if the quarks are massless, the single terms give 0. If they're not, they are there. Okay, but I'm not using massive quarks for the moment. So what is this p kappa? So p kappa now is the energy of the momentum p, energy of the gluon, 1 minus cos theta, right? And p bar kappa is the similar thing. So this is the angle between the p bar and the gluon, and this is the angle between the p and the kappa. So since if you have back to back, right, the angle, so you go in the central mass frame, this angle, right, is pi minus the other angle. So this one is actually 1 plus cos theta. So I get over, at the end, and this is CF alpha S over 2 pi sigma Born d cos theta d kappa 0 for 1 minus cos theta 1 plus cos theta. Okay? So the kappa 0 term comes from here, and you end up, so there is a kappa 0 square from here inside also, right, the modulus of k. So at the end, you're left with this term and this term. So you see that this is d kappa over kappa 0. So when the energy of the gluon goes to 0, this gives a log divergence. And when the gluon is collinear either with one quark or with the anti-quark, this also gives a log divergence. This and this. So this is called infrared, and this is called collinear. You have 2 points where you have a divergence. Okay, so actually there is a way to picture this. I'm not going now. I don't care very much. But now you see that I wrote this now already in the form such that I can combine with the virtual, because now this is an object, so it's an integral which is divergent, okay, and is divergent at the border of the integral, right? So this diverges at kappa 0 equals 0 on the boundary, and this also on the boundary of the cos theta, okay? So there is a divergence there, and what I can do, I can imagine, right, that my virtual QQ bar is minus sigma Born CF alpha S over 2 pi. So here I will get a divergence proportional to the Born. So what I can write it in this way. I can write it, I can imagine or guess, if you want, from the KLN theorem that the virtual cross-section has to have this form. Okay, so I imagine, so let's say, let me picture, I can make a change of variable, which is in the notes, and I can say that the phase space of 3 particles is like a triangle in 2 variables, which are the fraction of energy. So the virtual and the divergences live on the boundaries. So I can say, I can rewrite my virtual saying that the virtual in this phase space of a real sits in one specific point on the boundary as a delta. Okay? Remember when last in the discussion we said that the virtuals were the Born in the PT of the Higgs was at PT equals 0, and then when I added the virtuals, I added minus infinity here as a delta, and then I had to integrate to cancel the divergence. Remember that we did this in the discussion? That's the same. This is exactly the same as I'm doing now. I put in the virtuals in the boundary, and then I'm canceling the divergence with the real. So in order to do that, I actually need to go in d dimensions, right? But I'm not very much interested right now, okay, in the detail. The only thing I want you to notice is that also here, right, you have here you have a divergence, here you have the opposite divergence, and they will cancel. Yes. Sorry, it's summed because they are in two different places. Yeah. So I'm coming. Then basically what you do, we do like this. We replace in d dimensions, and this gives minus 1 over 2 epsilon. So let me write the result to be clear, and then I come to your question. So the real at the end is like the Born, Cf alpha s over 2 pi, 2 over epsilon squared plus 3 over epsilon minus, this is the exact result, and the virtual is the same, but the divergences have the opposite sign. Okay, yes. So I still need to regularize it, right? Because this is going to be divergent, this is divergent, so I need some regularization before I can combine them, and then use dimensional regularization. Okay? So then at the end, you see that the 1 over so the 1 over epsilon term squared is the region where is the point, really in phase space, where this IR and collinear divergent is both. So you get 1 over epsilon squared. Then these are either collinear or soft. And then you have finite terms. And the result is that the sum of the two give 3/4 CF alpha S over pi, which is a famous result. Okay, it's finite, it's ultraviolet finite, right? Why is ultraviolet finite? I mean, this we knew from the beginning. There is no ultraviolet divergence here, because we're making a QCD correction of an electroweak process at the Born level. So if I had a UV divergence, that would mean that I would need to reabsorb my UV divergence into the QC divergence into the electron cathode, okay? And we know that electric charge is conserved. It cannot be renormalized. It cannot be renormalized by QCD because these are two different gauge groups, so they are independent. The charge is conserved independently, and therefore there cannot be any ultraviolet divergence at next leading order. Okay, very good. So, as I said, as not proven but outlined, right? So, just outlined, we have a way, right, to show that the cross section gets a finite correction which is as proportional to alpha s when the sum real with virtual. Okay, now how do I interpret it? As I said, the easiest way to interpret this calculation is to say that I compare this number, this cross section, with the probability of counting the number of events with an hadron, at least one hadron in the final state, with respect to the events that don't have an hadron in the final state, total, right? All possible events, for example. Okay. Now, why I'm talking about this? Well, because now the question I want to ask is, okay, now how I move to the right, right? I should calculate next to linear correction and so on. But this game will never bring me anywhere in number of partons, which is sufficient to draw the diagram. However, I learned something very important. I learned that in the limit where the radiation is soft, I don't have to do any computation, really, because my amplitude factorizes in this way. So it turns out that this is true, right? And it depends only, right? So this term here depends only on what particles you have in the final state. So you can build a theory, a soft theory, where your Feynman rules, right? So you say that this diagram here, which is a coherent emission, is M hard TA G J alpha epsilon alpha, where J alpha, right, we calculated, is one of the two pieces of the iconal term. Right? So this is the emission from the quark, and this one is the emission from the anti-quark. If I emit from anti-quark, I have to put a minus. Okay? So that's a very simple Feynman rule that I can use. No algebra because it's multiplied. And so if I emit from a quark, if I emit from an anti-quark, I get a minus. And then the other thing that can happen in QCD is that I emit a gluon from a gluon. Right? That's also can happen. I didn't have a gluon now, but if I now want to emit from this diagram, I can also emit from a gluon. And here is the same rule. So here is TA, P bar, alpha, pk. And if you have a gluon, the rule is the same, where instead of having the color representation in the fundamental, you have the color representation in the adjoint. Okay, because now you have three adjoint indices here. So I hope you remember, right? I mean, when we define SU3, we define it in the fundamental, but you can also write it in the adjoint. Where F, capital FA is just I, F, B, C. So the matrices in the adjoint are actually the F, right? So, and this becomes the Jacobi identity in QCD. So it's a nifty way to understand that the rules are all the same for everybody, okay? It's only change the fact that here you have an index because these are three vectors. But the only thing that changes is the charging color in front. So a gluon lives in the joint and therefore as an F. Okay. So now you have imagine that I want to iterate, right? This here. Well, I can emit, right? I will emit. I have a possibility of emitting from this gluon, from this quark, and from this quark. Not from this one internal. Right? So I only use the external particle to build this limit. Only the color of the external particle I need, okay, and the momenta. So, in other words, you have a way that given the particle and how they are actually connected in color, I'm not going to discuss this, but it's a very interesting part, right? I mean, remember that a gluon is like a double line, right? So there is a color connection. So the algebra of the color becomes non-trivial and gives correlation about different partons. I'm not going to discuss this in detail, but remember, right, that given that these rules have a color structure, this also intertwines with the soft limit. Anyway, so my bottom line here is that whatever Feynman diagram I have, I only look at the color of the external line and how it's connected. I need a color connection. But then I can build the soft radiation out of it. Okay? I can iterate using this and then a next step, and so on. So by doing this recursively, of course, this will work if at each step the gluon is softer than the softness of the gluons that I had before, right? Because this is a soft limit in step-by-step process. Okay, so let's see now. There is a there is another catch which is actually pretty interesting. So this is easy. This looks easy. However, there are two problems here with the soft that I somewhat sketched. But somewhat you always need, so imagine that this is a quark. You need to know if this quark is color connected with this one or is color connected with this one. So you need to know the color connection of the particle to use this limit. And the soft radiation, by definition, is a coherent process. So there is no sense in which really a gluon is attached to either of the external particles. What the gluon is attached to is the color flow of the particle themselves because of the matrices here. Okay, so again, here, for example, if I now attach soft radiation to this process, I can attach it to this line or to this line. But there is no meaning in saying that I attach it to this gluon because it is attached to both at the same time at the amplitude level, and then when I square, it will interfere. So a soft gluon is non-local, is a coherent object. Okay? So soft radiation is non-local. And that's obvious from a physical point of view, right? Because a wavelength of a soft gluon doesn't see, right, the internal structure of a Feynman diagram at high Q square. Okay, so having to base the evolution of final state on soft is complicated because it's a highly quantum process. Okay, so my goal, my hope to get to that point is to transform a quantum process, which one day we will be able to simulate on a quantum computer. That will be the perfect thing to simulate on a quantum computer, a la Feynman, let's say. Okay. However, now my goal really is to turn a quantum computation, right, which means summing over all diagram and squaring, into a semi-classical computation. Because a semi-classical computation, I can put it easily on a computer, because it will be step by step then. Okay? So now, how can I turn this computation into something classical? Classical-ish. Okay? So I go back to my cross-section, and I rewrite my radiation in this way. Same as before, right? There is a 4, 1 minus cos, I erased it, but anyway. So there was 1 minus cos theta squared, 1 over kappa 0, right? It was 1 plus times 1 minus, 1 minus cos theta squared, which is sin theta squared, right? But what is useful for us is to rewrite this thing here in this way. Bless you. No, because this is 1 minus cos theta squared. I break it in two, and I reintroduce the theta bar of before. Okay, nothing new, but I transform a product in the sum of two pieces, and each one depends on its own angle. So I rewritten the radiation of a soft gluon in terms of two pieces, right, and the cross-section level, right? So now I have one piece, which is the Born, okay, CF alpha S over 2 pi. If you want radiation term from the quark plus radiation from the antiquark and the amplitude level and the cross-section level. So now I transform this object as a sum of two squares. One square is emitting collinear radiation and soft from one leg, and the other one is emitting from the other leg. Okay, so I broke it in two, and then I'm gonna define an object which is Z, which is the fraction of energy of the gluon with respect to the total initial energy. And then so this is 1 over Z, right, term here. So I rewrite my cross-section in this way. As a sum of two pieces, right, I equal 1 and 2, where I have 1 over minus cos theta, 1 over Z, and then I correct, allow me, right, to reinstate. So remember that this thing was the soft limit. So there might be a polynomial on the numerator. So I'm only getting 1 over Z term from this computation. So I'm cheating and telling you that there is another piece, okay, which is here, and this piece is from the non-soft part, okay? So if I did the collinear approximation, I will also get this piece here. So I didn't get it from a computation, only I got 1 over Z because it was soft. But if I don't make the soft approximation, I also get a polynomial in the numerator. And then I call PGQ. So this object now is PGQ. So let me put an arrow to remind you that all the splitting functions, you have to read them the other way around, right? So when I talk about PGQ, it's actually a Q emitting a G. I don't know exactly why this. That's what it is. So now this example I've shown now that if instead of being soft, I use the collinear approximation as my ordering principle. So each one has a Z itself, right? So if instead of parameterizing my radiation in terms of soft, I parameterize in terms of linear, now I gain a non-quantum picture, classical picture of radiation from each line, and is local. So remember, soft radiation is not local. I don't know where it comes from because it's a coherent effect. Collinear radiation, I know where it comes from. I can label it parton by parton. I'm only using the external partons, but I know where if a collinear gluon comes from one parton or the other, because it's labeled with that thing. And since it's collinear, right, I know it's coming from there. So collinear radiation is local. So what happens in general is that any parton branching that you have in the final state, you can associate it to universal functions, which are called Altarelli-Parisi splitting functions. So a radiation that carries fraction of the momentum z. Okay, so you have a parton here, which is my mother. Okay, and the mother carry an energy E. So in the collinear limit, the virtuality of this object is small, and the fraction of energy taken by a parton, I call it Z. And then I have all possible splittings, right? So I have a quark that splits into a quark. You see, it's the same as this one with Z minus Z. So I plot it this way. And so on. Okay, so there is the P QG. So this is a gluon splitting into a quark. This is symmetric, and there's no pole. There is no soft divergence here, right? I mean, if you have one of the quarks that goes soft, there is no divergence because there is no Born, right? Because a gluon cannot go into a quark and that's it. So what there is no Born on which to factorize. And then if you have a PG, a gluon can go to a gluon. This is a bit more structured. And this is a gluon splitting into a gluon. And since the gluons are identical, this has to be symmetric in Z and into 1 minus Z automatically, obviously. So why this is interesting, as I said, is universal. And how you can think that is universal? Well, because there is this factorization, in this case it's called collinear factorization, and it's based on this simple idea, right, that if this intermediate particle is going with small virtuality, so if these two particles get together, the invariant mass of them is small, so the matter has a small invariant mass, but by the determination principle, having a small invariant mass means that it has a long lifetime, right? Its mass, its virtuality is small, so it lives longer, right? Because its on shell will be 0, but it has a small off-shellness, but it lives for a long time with respect to the hard radiation, which has a high Q square and lives for a short time. So what I'm really talking about here is a factorization in time, right? Is the hard scattering happens on time scale very short, and then this parton showering thing, this collinear radiation happens way after, because I'm really expanding in a kind of a time variable in a classical way, because I'm factorizing squares of amplitude. So there is no quantum anymore. It's really a classical process where time goes by. Okay, in fact, it's even more interesting because a very special one, in the sense that I told you that each step depends only on the external particle which are in each amplitude. So it doesn't depend on what happened before. It only depends on the state of the system at that given time. Okay? So these amplitudes get a new life at every branching because their past is erased, right? It's like having a new life every time you did something wrong, but it's erased every time. There is no memory of your past, and this we call Markovian process, right? A stochastic process for which the state of the system in the next step depends only on the state at the beginning, but not how the system got there. Okay? Yes. Thank you. Any other mistake? Blunt? Okay. So this is our picture. So now we are all equipped to build a multi-step process where at each stage particles are flying away, right? And then they have a probability of branching and so on and so forth. So we now need to build a stochastic process. So let me write the factorization first in general. So I can always write at the square level, right? This is the hard part, right, with respect to a given scale. And this is dt over t. I will tell you what t is. d phi over 2 pi alpha s over 2 pi pji of v. Okay, so what do I use for t? Now, t is related to the virtuality of this particle here. Related. But since, you see, I have a log measure here, is dt over t, it doesn't depend on what kind of numbers I rescale t with. That doesn't depend on energy, right? So this is ambiguous by definition, this object, because I can put 3 here, divided by 3, so this variable is the same. So there is an ambiguity on how I choose t, and there are various ways of doing that. The most natural one is the mass of the q square of the matter, but it's not the only one. Okay, so this is called the shower evolution variable. Okay, so it's a collinear evolution. And for example, m squared, you can rewrite it like 1 minus z theta squared e of the matter squared. You can just take the kinematics, right? You parameterize the two. So you have the matter like this. You have two angles, B and C. You can work out the kinematics yourself. This is the theta here is theta B plus theta C. It's very easy, kinematics. You can show that you can rewrite this way. And yet you see that when I take the ratio, right, in this measure, all the coefficients that don't depend on the energy, or this is a fixed number, on the angle, right, cancel. So what is the difference? The difference is in the soft behavior. So you can write, you can write any number here that you want, for example, and this is still a valid shower variable. So the difference among the showers, for the collinear is the same, but the differences are in the soft limit. Okay, So if we have the time, I'll explain. So one you might ask, is there a better one, right? I can choose, for the collinear limit, I can choose any of them, but is there a best one? Is there a right one? Okay, so then we will answer in the following, hopefully. But basically, at this level, I cannot choose which one it is because I don't have enough information to choose the best variable. It could be the angle, right? So in the evolution of the angle, in this case, the angle, since it has to be more collinear than before, if I choose the angle, then the next splitting has to be closer than the previous one. Okay? Oh, because it's an iterated limit, right? Whatever I choose as a soft, it has to be softer than the softest of the previous step. So it's a strongly ordered cascade. And then if we want to iterate, right, I can iterate this formula now. Next step, I make another one, and I make another splitting. The only condition I have is that it's strongly ordered. Okay. So what I get, I can now make the compute the result of this iterated splitting, approximated, in a way which we call a leading log approximation. So if you use theta, right, if you use the angles as ordering variables, which is, by the way, the right thing to do, and you have a cross-section for m particle, and you add kappa gluons of partons, this will be sigma n times alpha s to the kappa, and then you will have the integral at any given scale of each splitting. So each splitting gives you a log, right? And sorry, I still have to do the integration here. So this will give you a log to the kappa. So each one, right? Each of the splitting gives you, when you integrate over this phase space of this one, gives you a log, right? In the boundary of the phase space, n times iterated. So all multiplication of these logs. So the idea is to resum this log now. So what I do, I define a probability which is a sum over possible splitting dt over t, the integral in the z in the phi, alpha s over 2 pi, the probability, the splitting function of A going to C, and this is the probability, the emission probability of between t and t plus dt. Okay, so I call this differential probability is the probability of one emission, of emitting, in the time interval between t and t delta t. So then I can define 1 minus dpt as the probability of not branching or not emitting between t and delta t. Okay, so this is prob differential probability of not emitting. T in the interval T and dt. So now what we need to do is to, so follow this up a bit with attention now, because you have to follow what are the objects to understand. Remember, so P is the differential probability of emitting at time t, basically, okay, between time t and time delta t. So now I want the probability of non-emitting in a finite interval between q squared and t. So now, before I go on with the formulas, let's stop 1 second, otherwise we don't, we don't understand. So you should have asked, what does it mean to go from high virtuality to a lower virtuality without emitting? So if I branch, I go to a lower virtuality, right? That's obvious because I'm branching, no? So I have 2 partons instead of 1, and then I follow each parton and the virtuality has gone down. That's okay. But if I'm not branching, how can I move from one virtuality to another? That doesn't make sense. So it must mean that I'm thinking about something and I'm not telling, right? So so if you have a particle with a given virtuality here, right, you branch, and this one, Q2, is smaller virtuality than the other, the mother, okay? That's okay. But now, if I say that I'm not branching, how come that this one is a smaller one? The one I'm really saying, without having said it, but then I'm stressing it, is this is the probability of not branching in a way that I can see it. Okay? So this I have to include all the branching that I don't see to be infrared safe. Okay? So what I'm really calling this delta is the probability of going from one virtuality to a lower one, a finite amount, with no visible branching. So from the diagram point of view, I will have this one plus anything which is real, but whose energy or radius is such that I cannot tell, okay? I cannot tell that this gluon is different from the quark. So with respect to my detector resolution, I cannot distinguish a quark from a quark plus a gluon if the energy is lower than the threshold or the angle is smaller than an angle, right? So this is really, this thing here, as in its guts, the virtual, and the part of the real that is needed to cancel the infrared divergences, collinear and soft. Is that clear? So this is super important because otherwise we don't understand what we are doing. Okay, so it's really like, it really means, I don't know, pictorially you can plot it this way, right? Stuff that doesn't pass a threshold, that you cannot see. Okay, so the division between these two again depends on the scale. Okay, technically. Very good. So now we do a next step. So how do I compute this delta? Well, this will be, so a delta in a finite range will be the multiplication of this probability local of not branching n times, right? So this is between t and the t, so I break this distance in small pieces, and each one has a probability of not branching. Times the integral of before, this one, okay, which I'm not writing. So this is the product of kappa on each piece, right? So you have a long distance and you break it in this way. And each one has not, if you go from here to the end, I need not to branch in a resolvable way in any of the interval. So I multiply the probability of each one not branching. And this is the exponential of the sum, if these are small numbers. The exponential of the integral from t to q squared dt t prime dv d phi 2 pi alpha s over 2 pi p. Okay, and this is x of minus from q squared from t to q squared of dp of this one. So I define what is called famously the Sundakov form factor, which is the exponential of the integral of the local probability of branching minus. Okay, so this is an analogy, if you want, with the decay of a radioactive nuclei, right? Which is the boson or radioactive sample, a sample of radioactive nuclei. So you can make a one-to-one correspondence, but in the end, you need to integrate. So in a radioactive nuclei, you would have exp the integral from 0 to t lambda t, right? So if your probability of disintegrating in 1 second is lambda, right? If you want your nucleus to survive for a time t, then the probability is this one, is the Sundakov. So you have to integrate your probability over time. Okay, so this is lambda dt, sorry. And if lambda is constant, you get lambda t, right? So this you get exp of minus lambda t. So this is the survival of a nucleus up to time t. It's the same thing, it's a Sundakov. Okay, so that's for a parton is the same. So the probability in time of disintegrating is a probability in virtuality, which I have to integrate in the range of evolution that I have. It's the same idea. Okay, so this Sundakov is the basis of a parton shower, because now by using the probability, this probability of not branching, so again, I repeat why I'm using the probability of not branching, because that one is as in its guts all the corrections from virtual and real. So is the thing that contains all the physics, the most important part of the physics. Yes. It does not have the hard part, but it has a piece of the hard part in the collinear. So it's not soft. So it's not soft and collinear. Right? The collinear part is in the numerator of the splitting function. That part in the parton does not need to be soft. It can be hard and collinear. That is there. Yeah, yeah, this is right, because there is no collinear. Yeah, it's suppressed. Yes. Enhancement with the log of the mass. Yeah. So I mean, if you have a massive particle, you still have the collinear logs, but they are screened by the mass. Okay. But if you get, it depends how hard. So if you have a top just at 100 GeV PT, right, there is no collinear enhancement. But if you have a top at 10 TeV, right, then this log is large, and then you have to sum the log anyway, even if it has not lambda QCD as a cutoff, but it has the mass on the top as a cutoff. So we introduce a fragmentation function for the top, and we resample the large logs also for the top. And it really is a game of scales, right? So if it's a massless quark, it means that the scale, you have a PT scale over lambda QCD, okay? So that's the log that you're resumming. If you have a massive quark, the log that you might need to resum is PT of the jet, the particle, over the mass of the quark. If this ratio is large, then you have to resum it with a fragmentation function, which is the same thing as this one. Okay. Yes. So Q is the starting scale and Q naught is the finishing scale. Okay. So let me show you one thing, and then we'll be hopefully more clear. Is the same thing that you're asking. So now I want. So let me give you the picture. So now we check unitarity, and I hope. Okay. So at the end of the day, if you sum everything that can happen, you have to get 1. Right? So this is a probabilistic algorithm. So if you really are able to compute all possibilities and you sum them, all the sum of all probabilities has to have 1 because something will happen. Okay? So now you can do it. It's actually interesting. So the probability of emitting a particle at time equal t equal 1 in the evolution is equal to the probability of not emitting anything up to T1, the probability, this probability density, which I draw this way to remember myself that is a density. So it's the probability of emission at a given time is T1. And this then is the probability of not emitting up to T. So this is the probability of having one emission in the interval. This is a local probability of emitting at time t1, but since I want the probability what happens in a given interval, right, I say that the probability of emitting only one gluon resolvable when I go from Q0 and Q0 and from Q to Q0 squared is one emission at some point and no emission before and no emission after. And then I have to integrate over T1, no? Because I can emit at any moment. But now you see that this thing here, how in the way that is built, the Sudakov form factor, they combine, right? Because they are multiplied, but then there is an integral in the exponential, so you combine the exponential, and then some of the product of chained Sudakov, you get the total Sudakov in front. So this is the total thing of not emitting at all times one emission at T1. And then I will have to integrate over T1. Two emissions is the same story. So I make two emissions, one at T1, one at T2, and now you got the point, right? So it's non-emitting up to T1, emitting at T1, non-emitting, and so on, right? Then I emit at T2, and then I have the Sundakov at the end. And these I combine the Sundakov again, and then I have to order them, right? Because this happens before the other. So when I do the integral, then this happens before. I decided that it happens before, so I will have to take this into account. So at the end, you will have that T1, Tn, these always combine in one number which is in front, which is always the same, right? Times the probabilities of emission local. TL, and then you have an ordering. Right, use the theta function to say that they are ordered one after the other. Okay, but the nice thing is that they all have the same structure. Not emission from beginning to the end, right? Times all these single emissions ordered in time. So this you integrate this one, for example, over the T1. So each one, right? I mean, so you have to integrate. So you have to integrate this up to here, but this moves and so on. So you have all these integral possibilities, and the result is a Pn, the integral here, I call it Pn, is delta of Q square 0, 1 over kappa factorial Q0 d P of T. N. And now I sum them, and you see what I get, right? Because this get an exponential with a plus, this has an exponential with a minus, and then I get 1, right? So this gives me an exponential with a plus, times exponential of the integral of dp t from q squared to q0, which is 1. So at the end of the day, right, you have something which is unitary. So whatever happens, right, has a probability, right, which is a Poissonian probability now, right, is like a Poissonian. There is this exponential in front times lambda, right, to the n, and each lambda to the n is the number of emissions. So now this is a Poissonian distribution, and when you sum and you integrate a Poissonian distribution, you get 1. Okay, so why this is so we have phrased it in a way that is probabilistic. So I repeat, is probabilistic and is classical, because again you don't need to do anything quantistic. You just go with the probability which is classical. Okay, there are no amplitudes. You always work at the amplitude square level. So how does it work at the end? So now you do the following. You have an algorithm which is called a Parton-Shovel algorithm, which tells you pick a random number. Right? That's why these are called Monte Carlo. Okay, you pick a random number between 0 and 1, and you call it raw. And then you solve delta q square q0 square equal to rho. Right? Remember, if you want, so you want to generate a probability of branching, right? So what you need is to invert the primitive of your PDF. So remember, if you want to generate a variable, a random variable, following a given distribution f, what you have to do is to calculate the integral of f in a generic way, the primitive of x, and invert that, and throw a random number through the inverse of that primitive, and then you get the value which is distributed as your function f. Have you ever done this in your life? I hope so. If not, look it up. I mean, the difficulty is that we don't know the primitive of all the functions, right? Like here, right? The Sudakov, we have to invert it numerically now. So we say, well, it's a number, right? So I random number. Then I have to solve it backwards, right? I solve it, I determine Q, 0, and that's the scale of branching. So I randomly generated a scale of branching using the Sudakov as a probability of generating that scale. Because my probability is P, which is the inside the Sudakov. So if the solution Q0, so let me not call it Q0, because let me call it Q. Okay, so I want so I have my hard scattering is a Q0, and my n is a Q square, and my n is a Q0 ordered lambda QCD. Okay, so I'm starting from the mass of the Higgs, and then I'm arriving at the end, which is lambda QCD, and I cannot do anything more perturbatively because this whole story is perturbative, and at that point I cannot do anything anymore. Okay, so this is my extreme limit of the evolution. I cannot go beyond this, and typically I stop at 1 GeV. So the showers are stopped around 1 GeV. Okay, so this is the older way. So I generate a random number, I solve, I find Q squared. If Q squared, small Q squared, if small Q squared is above Q0, I generate a branch, I associate a branching at this scale, okay? I generate a Z fraction of momenta following the Altanelli-Parisi splitting function distribution, okay? And then I have an event, I have the Q square of the event, the Z, I generate phi, and then boom, I transform one Parton in two. And then I do it again, right? Then I generate it again, and I move like that until I get a number, right? A random, a Q, which is lower than lambda, and then I stop. Then the evolution is over. So this has two effects at the end, right? We have resummed the logs. So the accuracy of a shower in this region of phase space is higher than a fixed order computation, because in a fixed order computation, all these logs are explicit and not resummed, while if I put in the exponential, I have resummed them. So I resum the large logs. So in this region of the phase space, the shower is more accurate than a fixed order computation. When the jets or the partons are hard, it's not true anymore, because there I should use a matrix element, no? A fixed order computation. So over the years, people have figured out the way to actually merge these two methods, right? To use a matrix, at least for the first branching, to use a matrix element, hard matrix element here in the phase space regions where all partons are hard, and to use a shower to cover the rest of the phase space where most of the partons are collinear or soft. So this is called merging, and there are a lot of techniques and improvement over the years, and a full technology. So this is how all the Pythia, Herwig, Sherpa, all these Monte Carlo work together with matrix element generator like MadGraph or Algen or other codes which compute instead the matrix element a fixed order. Okay. Yes. Ne? Well, that's very easy because you are only um, only getting the leading logs, the logs which come from a next to leading order computation, right? You get what are called the leading logs, right? The first, you get the logs of this first branching. So all your shower, so let me explain this way. So imagine that you do two branchings, okay? Okay, so what I've been explained today is that the region of phase space where this angle, 1, is much, oh, well, let me draw it here, which is easier, is much bigger than theta 2. And then this is, if there is another one, then is much bigger, so it's strongly ordered. If it's strongly ordered, you are doing a leading approximation. You're breaking it here, and you are iterating these three, and you're keeping only, right? So here you develop a log. This you develop a log. Here also, you're taking the log of each one. So your expression in each perturbative order is alpha s to the n log to the n. Okay? You never have the so-called sublead. So the expression they're using is like this. For each alpha s, there is a log. And this we call leading log. But now, if you think about, right, there is also regions of phase space where this is like order of theta 1. So it does not develop a log. So you also have things which are alpha s n log to the n minus 1, right? Which we didn't include because in each piece we had the log. But in general, they might not strongly ordered, right? So if not strongly ordered because of one, you have a subleading log. If two of them are not ordered strongly, you have two, and so on. But in order to do this, you need a splitting function which you know not ordered 1, 2, 3. So you need another object. You need something like this. For example, which becomes this in the limit where the first splitting is larger than the second one, you get the iterated one. But this object in general will have all the orderings, right? So if you want to have this accuracy, you need a splitting function which is 1 to 3. Because you also have the ordering, I don't know, that theta 2 is bigger than theta 1. And then you have only one log. for example. So in each iteration, you get subleading logs. But to do that, you need a higher a next to leading log computation of the splitting function, if you want. Right? Yeah. Okay. Yes. Yeah. Right. So I left out two very important, well, three very important points. So let me only mention them. Right. So what happens? So what we discussed now in this example is here. So what we discussed is this region here today, which means you start from the Higgs and then you evolve down to roughly 1 GeV. So we are missing how I go from many partons to hadrons and how I go from the proton to the Higgs. I didn't discuss this part. So this is called final state radiation. And this is called initial state radiation, is in the notes. And what you really do here, so here you go forward in time up to hadronization. What you do here in a shower, you go back in time. Why? Because if you were going forward in time, you would never end up in a Higgs place, because you would end up everywhere. So that would be a bad idea if you want to simulate Higgs. So to simulate the Higgs, I go backwards in time, and I do the backward evolution weighted by the PDF. It's explained in the notes. I hope I don't have the time to go through it, but you do exactly the same thing. But now, when you go backwards in the branching, you take into account the evolution of your PDF. So you deconstruct the PDF back in time. The PDF, remember, you take a low energy scale, right, and you evolve it with d up to the mass of the Higgs. And what you do in a shower, you do the opposite. You take the probability and the mass of the Higgs, and you decompose it with probability of branching backwards in time, using as a weight the PDF. So if you want, right, I always give this example, and then I come to the hadronization. I haven't forgotten it. So the example of a shower is like I told you, a shower associated a story to an event. But where does it start from? It starts from, let's say, like me. If you had, so take myself, the story of my life, and you put me here, okay? And this is the Higgs scale. And then the shower says, okay, I want a Higgs, right? So I want to generate a story for Fabio. I don't start from all possible babies in the universe until I get to Fabio, because it's not going to end well, right? So I start from Fabio in the middle of the shower at high Q squared, okay, at the top of your Q squared. And then I start from there to associate a story. I simulate the future of Fabio, disintegrating in many pieces in the universe, right? So I get old, and then hopefully, and then blah, blah, right? And this is my future. And my future, in the future, my virtuality of each of the partons in which I disintegrate gets smaller, right? The story goes from high Q squared to lambda QCD here. And then when I arrive here, I attach a model where all pairs of quarks get together into hadrons. And that's called hadronization. Why I can do that is because I'm using this variable as an evolution variable, which is the angle. So if I'm using the angle as evolution, the farther I go with lower Q squared, the closer are the partons in my story. And when they're close, I can get together in the color singlet without any major effort. So the color singlet are all closed in phase space at the end if I use angular ordering. And that's why the annotation model works. Because then I don't have, imagine that I have a model where I have a quark which is color connected with a quark which is going the other side of the event, then I will be stuck, right? But if all the particles connected are closed, I can do an annotation model. And that's what we are doing. And then I take my picture, I go here, I get my picture and say, how, you ask ChatGPT how I would have looked 10 years ago or 15 years ago and back when I was born. And now with ChatGPT you can actually do it, right? So, and then you go back, and this is the backward evolution. So you ask the shower to reconstruct the event in the back in time. So this is this here, q squared is positive, is a time-like evolution. Here, q squared is negative, is a space-like evolution. And the reason is obvious, right? Because when you have a quark, you have a quark from the proton, right, which comes at zero virtuality, then emits, it splits. This has no virtuality, but this one now is a T-channel, and is a virtuality which is less than zero. Then it splits, it has a virtuality Q1, so this is Q1, Q2, less than zero, and in modulus larger than this one, okay? And then you arrive that this has a virtuality, okay? High q squared, and then you evolve it the other way around. Yeah.
I don't really know how to picture the like this backwards process, because like if we have it in a final state, I mean we start from one state and then we get all of the final states. But if we do it backwards, we start from one, but still the initial state radiation is a lot of like final states, right?
Well, so you have it. So let me take the let me take the gluon that enters and makes the Higgs. Right, this gluon. This one, in our computation, we put it on shell. But in this story, it's not on shell. Okay. In fact, in the shower, it's not. Okay. The shower, every time the shower advances or goes back, it changes the virtuality of the particles. Because at each step, you have to readjust the virtualities. So this guy, the right way of thinking about it is that it has a virtuality of order of the mass of the Higgs, minus. In our calculation, is on shell, but in the story of the event, no. So then this is a high virtuality, and you have to connect with the quark in the proton, which has zero virtuality. So the way to do it is that these emit a photon, gluon, and it gets lower. Okay, so let me use q squared, which is negative. Okay, so this one is 1, and this is lower in modulus. Okay, so this is smaller. And then you do like this, and this is also smaller. And so on. But they're all negative. So when you go at the beginning, so you end up, and when you end up, they have no virtuality. That's the way it goes. Here is exactly the opposite. We think of them on the final state on shell, but it's not true. I mean, when they branch, they get virtual. When they branch again, Pythia rebuilds the virtuality of the first splitting and gets more. These objects are all very virtual. And then they are less virtual. So that's the true, that what happens really. The fact that we are using on-shell amplitudes as intermediate states is our limitation and our inability to do computation with off-shell lengths, right? Because the off-shell amplitudes are not gauge invariant, for example, in SO3, so you cannot use them. So we use all on-shell, and then we correct them in the shower. But you have to clarify your mind. All the partons here are all of shell, all of them, in the true event. Yeah. No, we still calculate with the all shell, and then we correct the kinematics with off-shell kinematics. But the calculation is always on shell, because everything I explained here, everything is massless, right? Everything is on shell.
So it's like you're not adding partial shower on top of fixed order, but we do it simultaneously.
No, we use the probabilities. So these are all probabilities, okay? So all the probabilities are calculated with on-shell amplitudes. But when you then say, right, that this is L, nu, pion, blah, blah, then you go back. So suppose that your shower has gone to the end. Then you have 1,000 pions, okay? But you have all the story of your event, because in the PC output, you can rebuild all the story, all back to the beginning. You have all the branchings, everything is there. So you say that you have a pion of that is going this direction, another pion that goes in the direction, and originally they were coming from the same parton. But now it's obvious that if this has 10 GV and is going this way, and this one has 10 GV going this way, this object is off shell, right? And so on. So kinematically, they are all off shell, all of them. But when I computed the probability, I used only on-shell amplitudes or on-shell splittings. Then I correct the kinematics. So I'm using the probabilities from on-shell, but the kinematics is correct in keeping off-shell quantities. Yeah, this is something that confused people quite a bit, because I mean, at the end of the day, what you really like is that you compute the whole history, right? Really, from the beginning to the end. That what we would like, but we cannot, so we break it, and the only way to break it in a consistent way is to have amplitudes which are on shell. So I haven't talked about other things, but at least you have the notes, so there are many nice lectures on the web too if you want to learn more. So we call it a day for me.